Exercises are to sort of warm you up to some of the ideas that we're going to be discussing today. This first set of ordered pairs, I mean, both sets are pretty small. They only have 2 ordered pairs in them. But this idea of for each x value, there is one and only one y value is going to be a very important idea that we talk about today. And everybody from looking around at the boards, at least the people that did the work on the boards, I can see that you have set 1 as your answer, which is true. Set 1 is the only set out of these two where for each x, for each value of x, there is one and only one value of y. This is going to actually be a definition today that we're going to see, that we're going to use for the remainder of the course, and then every math course you take from this point on will be using this idea, this concept. And then most of you successfully graphed the lines y equals 2x and y equals 2x plus 4. And I asked you to use the integers starting with -2. I mean, we could have used any integers. We just thought we'd make it easy. So your x values, your integers look like this. And the points you should have gotten should have looked something like this for each line. And hopefully you noticed that these y values for the second line are just 4 greater than the y values of the first line, because you still have your 2x and you added 4 to all of these y values to get the points on your second line. And I can see from the graphs on the board that you were successful with that. So this is an idea that's coming up in a couple of weeks, this idea of does this line change y equals 2x? And let me just quickly throw in a line. So here's y equals 2x. Roughly right there. And then the line y equals 2x plus 4 is exactly, grows at exactly the same rate. It's got the same slope. I get another line, but everything's just, all your y values are just exactly 4 higher. So it would be like that. And let's see if I can do this right. What was -1 at? 2. 2 is at 4. So something like this. Okay. Those two lines were joined. So there's just a distance of 4 between all your y values. Okay, now a lot of you recognize that this was absolute value, but it's not exactly the absolute value. It's the absolute value. And how has it been moved? How has the absolute value function been moved? Up 1, right? Because the absolute value goes 0, 0, 1, 1, 2, 2, 3, 3. So that entire graph has moved up 1. So even though I didn't ask you for it, could you figure out what the equation would be for that graph? And we would need something else, absolute value of x plus 1, right? Okay, is that right? No. Right, you take the absolute value of x, and then just like you would have done with the absolute value, here's the absolute value. Okay, and the only difference between this purple graph, which is the graph of the absolute value, and the blue graph is that all your y values have been shifted up 1. So if we call this y1, which is the purple graph, the blue graph, y2, is those same values, those same y values, and then you've added 1 to everything. You've moved it up 1. So that's what the graph, that's the equation for the graph of the blue lines. All right. Everybody was fine. What are the y coordinates? X, and then describe the x coordinates of all points on this graph. So if you look at this graph, you see that these arrows go up in both directions to infinity, which means that there's no restrictions on any of these x values. So the x coordinates that you can plug into this graph, the absolute value of x plus 1, is every single x that lies on this number line, every single x. And the way you represent that with interval notation is negative infinity to infinity. We call this the domain for this equation. It's all the inputs that you're allowed to put in, all the inputs, and there's no restrictions on them. We don't have any denominators to worry about where we have to worry about making the denominator 0. We don't have any even roots where we have to worry about not having the value under the even root be negative. We're pretty much home free here, okay? Now, to describe the y coordinates of all the points, we see that we have a lowest y coordinate, don't we? And what is that? 1. So the y coordinates are going to start at 1, and it includes 1, so we use the staple idea. But there's no bound. It grows forever and ever in a positive direction. So that's how we would describe all the y coordinates. They start at 1, and they grow forever and ever. And that's what we call the range. That's the set of all of our output values. So that's the range for this function. So again, remember, both the domain and the range are sets of numbers here. So every time you give an answer for a domain or a range, it has to be some kind of set notation, whether you use set builder notation or interval notation. Okay, it's always a set of numbers. All right, so let's start today. Let's do the demo where we're going to bring back some of these ideas that we've talked about, and then you're going to have some time to do your class activity. So want to start us off, Jenny? Okay. And this isn't anything new to you, but the title here might be new. The title here is relations. So this is the beginning of how we're going to define what a relation is in mathematics. So let's continue. Number 2. Want to go right around the table, Alex? Okay, thank you. So again, note, we're creating a set. How do I know this is a set from looking at the notation there? What do you see that tells me it's a set? The squiggly parentheses called the braces, right? So right here, this tells us we're looking at a set, and each one of these individual pieces of the set is an ordered pair, right? And what goes into this ordered pair? It's the name of the 2013 Boston Celtic player, right? That's the first coordinate, is the name of the Celtic player, and then his height is the second coordinate. So this is just a set of ordered pairs, and we just define this to be a relation. It's a set of any ordered pairs. So this is what we call, this is an example of a relation in mathematics. It's just a set of ordered pairs. Nothing special about it. You can create zillions of these, right? Any ordered pairs you want. So most of these people are no longer on the Celtics. I don't know if any of them are, but when I did this problem back in the fall of 2013, they were on the roster. Okay, so let's take a look at what we can do with this set. So Emily, you want to do number 3?
The set of names Jeff Green, Avery Pratt, Otis, and Gerald Wallace is the set of all first element inputs ordered pairs
Okay, so a minute ago we were looking at the graph of the absolute value of x plus 1, and we talked about the domain being all real numbers. Well, here's an example where we have a set of ordered pairs, and it's not about a graph, it's about the Boston Celtics, and the first component of each one of these ordered pairs is the name. So we call the inputs, or the first component in each one of these ordered pairs, whether they're numbers or names, the domain of the relation, the domain. Okay, Keith, Sam?
We also always think of it as x.
Yes, you could always think of it as the x coordinate, what you're used to calling the x coordinate. But sometimes you might be dealing with a relationship that might look like this. Distance equals 60 times t. So if you're dealing with a relationship like that, what letters would go inside your ordered pair? T and D. So you just have to recognize that x and y is what we standardly call the coordinates for any graphical relationship. But that relationship can be defined by other variables. So that's why we say here the first component of the input, because we don't always have equations that are just in terms of x and y. But that's typically what we call the x values here. Okay, so this is called the domain, and let's see what the set of heights are called. If we just looked at just the set of heights, want to continue with that, Ian? You don't have to go through them.
Set of all second components called range. Go 6, 9, which that's only plus not necessary.
Right. So all of the second components are the outputs, which, as Sam would say, you would typically call y. It's what we call the range. And on our absolute value of x plus 1 graph, the range was the set of numbers starting at 1 and going all the way out to infinity. In this case, it's these three heights. One of them appeared twice, but just like when we had the Beatles reunion, we didn't include Paul McCartney and John Lennon twice, just because they were in both sets, okay? So visually, this is what it looks like. You have an input. Remember, this blue circle here represents all your inputs, or your first components, and it's their names. And then the output is their heights. And each input goes to one and only one output, okay? Each one of these inputs goes to one and only one height. Person at any particular time can't be two different heights, okay? So we call this particular relationship a well-defined relation, well-defined. So because it's well, before we get there, I'm moving ahead of myself here. Let's reverse this now. Let's suppose I put the height first as my input, and then the name of the Celtic player as the output. So let's fill in the domain and range here. What would I be putting into the domain? 6'9" would be one value, and I'd put a little dot. What else? 6'2". I'd put another dot. Yep. Well, we don't do 6'9" twice, right? Because we only include it once. All right. So let's see. 6'2" would go to which player? Avery, yep. And 6'5" would go to Keith, yep, Bogans. And 6'9" goes to Jeff Green, and it also goes to Gerald Wallace. All right. So that's the domain and range for this relation. This is a relation, and this is the domain of the relation, and this is the range of the relation. All right. Okay, so now the end of the season comes, and we want to give out the most valuable player award. That's what MVP stands for. And it's going to go to the player who's 6'9". So I go to here, and I see 6'9". Who do I give the award to? Oh, it can only go to one of them. Which one does it go to? We can't give it to both. We split it in half. We'll cut the trophy in half, okay? Not well defined. That's what it says down here, right? So you can see here that in this situation, we have a problem. This relation is not well defined because we don't know who to give the MVP to. So this is an example of it's a relation, it's totally valid, but for our purposes in math, if we have an input, we need to know what the output is without any question. So we now create a new definition, and that's this word functions. And this is one of the major concepts we're going to cover in this class this semester, is the idea of functions. Okay, so Drew, you want to read functions for us? Okay, so that's the definition of a function said two ways, one with the words input and output, and one with the words domain and range. So if you look back to your preview exercises, and you look back to problem number 1 in your preview exercises, among your cells at your table, can you identify which one of those sets is a function from looking at your preview exercises? And when you agree, could you put up your flag? If you didn't get your flag, would you please get one? Oh, how are we going to, let's see, I would like one person who said set 1, just out of the table 1 and 3. Would one person volunteer to argue why they think it's set 1? And then one person from either table 4 or 5 argue why you think it's step 2. Do I have a volunteer from either table 1 or table 3? Doug's going to argue why set 1 is a function, and who's going to argue from table 4 or table 5? Sam? Sam's going to argue why he thinks set 2 is a function. So let's go back and look at, here's set 1, and here's set 2. So, Doug, would you argue why you think set 1 is a function? Okay, so if we go back to our pictures, domain and range, and we put in our inputs, which are, there's only 2 inputs, 1 and 2, and there's one output 5. If you're the input 1, you go to 5. So that's 1 and only 1 output for number 1. And if you're the number 2, you go to 5, and that's 1 and only 1 output. Okay, so let's try to argue. Someone's going to try to argue, Sam, for the domain and range for set 2, which looks like this. The number 5 goes to the output 1, and it also goes to the output 2.
Because it says actually in the function, well-defined relation or function has exactly one output value for any input value.
Okay, so here's my input value, 5. Does it have exactly one output value? No. So this is not a function. Here's 1. Does 1 have exactly one output value? Yes. Does 2 have exactly one output value? Yes. So number 1 is a function, and number 2 is a relation. In fact, number 1 is also a relation, but it's a special relation called a function. Okay, so it doesn't say that the output value has to be unique in the sense that no other input can go to that. Just like we could have 2 Celtics players having the same height, that was fine when we were looking. No, but that was when we had the heights as the input. This was okay. We knew Avery's height, we knew Jeff's height, even though Jeff and Gerald had the same height, it was okay. But when we reversed it and put the heights first, that's when we ran into trouble. This is not a function. This is a function. So if we, in this particular relation, the way the ordered pairs are arranged here, this is a function. This is a function because each input has 1 and only 1 output, but when we reverse it, it doesn't go the other way around. This is just a relation. It's not a function. because we had trouble trying to figure out who to give the award to, right? Not a function. Okay, so you'll have some practice with your homework problems with this idea of what makes a relation and a function a function. Okay, so now we're going to take a look at functional notation. Since this is a new idea, there's lots of ways to represent a function. We just saw that one way to represent a function with our preview exercises is with a graph, graphically. Sometimes you can represent a function with an equation. Sometimes you can represent a function with just words. And other times you can represent a function with a table of values. So this table below is going to give you the height of a baseball in feet, that's the units, at X seconds. So the values listed in the table above represent or define a function. If you give me a time, I can look at the fact that at 1 second, I'm at 67 feet above the ground. Okay, so that is well defined. I'm not at multiple feet above the ground at 1 second. I'm at one and only one height above the ground. The language that we use is we say that y, in this case, the height of the football, is a function of x, that we don't know what the height is until you come along and tell me how many seconds it has been since the ball has been hit, the baseball has been hit. So instead of using this variable y, we now are going to introduce some letters that are going to represent functions. These are the common letters, little f, little g, little h, big F, big G, BH. We could use other letters, but those are the typical ones. And to make it very explicit that the output value y, depends or is a function of the input value x, we use this new notation, and it's read f of x. Okay, this is the same. This represents an output value. So it takes the spot of y in your ordered pair. So now instead of x comma y, we would use x comma f of x. To really emphasize, this emphasizes the fact that the output value depends or is a function of the value of x. So that's what the notation means. So where you're used to putting the letter y, we now put f of x. And that assumes x is the input. If we had d there, it would be f of d. If we had s as the input, it would be f of s, whatever your variable is. We call this variable x the independent variable. It's free to roam over time. And the value f of x or y is dependent on the value of x. So that's called the dependent variable. Sometimes when students first see this notation, because you were trained so well when you first learned algebra that when you saw parentheses it meant multiplication, sometimes people think that some multiplication is going on here. But this does not mean multiplication. It simply takes the place of this language, f of x. Whatever appears in the parentheses is called your input, and what comes out of this f of the input is called your output. Those are some other languages for it. So for this function, my input is time in seconds, and my output is the height of the baseball in feet. So let's see how we would interpret this new notation. And it may be totally new for some of you, and many of you may have seen this before. So let's take a look at this. So notice it says evaluate each expression using the table of values for height of a baseball as a function of time in the table above. So this says f of 2. This is how we read it. F of 2. So what that means is 2 is my input value or my x value. So how do I find the output that's associated with f of 2? What am I plugging it into? Hang on, one person at a time. Yeah, but I don't have an equation to plug it into. I look at the table of values. So let's go up here and look at the table of values. And here's my 2. And thank goodness I have one and only one output. And now I can define what f of 2 is. I put the number 99 right beside this. Okay? So f of 2 is exactly the same as the number 99. So if I were creating a set of ordered pairs, I could do that. Excuse me? Oh, okay. About plugging in. Okay, thanks, Alex. Sorry, I misunderstood you. And that is equal to 2 comma 99. I see. So you were saying plug the 2 into here. Diagram f of input equals. Yeah. Okay, thank you. I'm sorry I didn't understand you. Okay, so this is asking us to find the output when the input is 2 seconds. Okay, so if I asked you on your quiz or your final or your test, whatever, to interpret this, your input is 2, it's given, so you would say at 2 seconds, I mean, there's lots of variations of how you can say this. At 2 seconds, the height of the baseball is 99 feet. Notice you can see each of the input and output values along with their units. So every time you write a sentence, you should see both of the values, your input value and your output value, along with the corresponding units. Okay, f of 0. What's f of 0 going to be here? Okay, you go to 0. Oops, it's supposed to be. Oh. Oh, why isn't that letting me, getting all these beautiful colors. Here we go. So I want the yellow one. So here's 0. 0 is our input, right? 0 is the input. So I go up to my table to 0 seconds. And what's the output? 3. Okay. Did someone think it was something different? Okay. Okay, so here our input is 0 seconds and the height of the baseball. So that means probably just before the baseball player was going to smack that baseball, right at the point of impact, the baseball was 3 feet above the ground, right? So the baseball, so at 0 seconds, and most of the time, when time is 0 seconds, we use another word for it, initially. So you can say at 0 seconds, or you can use this word initially. That means the same thing. It means t equals 0. Initially, the height of the baseball, we can use the same sentence all the way across now. The height of the baseball is 3 feet above the ground. Okay. So anytime t equals 0 or h equals 0, whatever your input value is, the variable, you cannot use the word initially. But you don't have to be fancy like that if you don't want. You can just say at 0 seconds if you want to.
Is that only for height?
No, it could be height.
Height of something. So anything as a function of time?
Yeah, usually a function of time. Yeah,
So
we say initially.
initially
Yeah,
is-
this time.
okay.
Yeah. So like if you look at a quadratic equation for throwing an object, you get something like this. F of t equals, you use this type of notation. This little sub naught here means initial height. And this little v naught means initial velocity that you throw the object. Okay, so now how does this next one differ? Right, so here, notice we're giving you what is the output value, what we typically call y, and we're asking you to find the x. So where do you go in your table to find the 103? On the top, right. So now we're looking for the top output, 103. Here we found it, and there's the input. So now look at how your sentence changes a little bit. Because I'm given 103, you can say now, when the baseball, because that's the value you're given in this expression or equation up here, when the baseball is 103 feet above the ground, how many seconds was it above the ground? 2.5 seconds will have passed. There's lots of ways to say the same thing. That's just today how when I do this for my 1040 class, I'll probably say it a little differently. Okay. Any questions on interpreting functional notations when you have a table, knowing what each of these values now mean? Sam?
I never quite understood why, since it's generally understood that the y is the value of the function of x. So why do we have to use f of x notation if we understand that y is output of x?
It's just to be more explicit that it is definitely a function of x, and this is just the notation that mathematicians use. You're right that.
So I'm kind of confused because I've known that y is the output value in my head. So.
Well, because you can also have a relationship like this, y equals x squared. Well, I can't even say it. I'll show you later. Okay. I don't want to get anybody messed up. Okay, so let's take a look at your class activities, because this is it for today for the demo. Your class activities are going to have you work with all of the new ideas from today, domain and range, whether something's a function. It also is going to have you learn a test, a visual test for functions, and you'll be using graphs to interpret functions. So your class activities, I hope, should go pretty smoothly for you.